This is the second video in a series in which I am putting together an assembler for the Signetics 8X300 microprocessor. If you saw the first video, then I briefly went through the software to demonstrate how I was writing it and what it was for, and I've been asked to show a bit more detail about the inner workings of it. I still won't go into a massive amount of detail, but I will clarify a few of the points as to exactly how the software structure works. So this is the tool as it stands at the moment, and I wanted a graphical interface rather than a command line version. It's just much easier to use, and also I wanted it to be a kind of code editor as well, but it is an assembler, it's not a compiler. So we'll have a look at the software and see how it's structured. So it's written using Ball and Builder, and actually using C++ to create this particular tool. So we'll go through the software in a bit more detail than last time. If software is not your thing, then feel free to skip this video, and in the upcoming videos then we'll look at actually writing some code for the 8X300 and then looking at the logic analyzer series, which is what this is all for in the first place. Okay, so the software is really based around a series of arrays, and the arrays consist of arrays of structures. So if we look at this first one, we've got a structure that is defined as an array of characters that is 6 bytes long for each of those particular character strings, and that is to hold the actual text or the characters that will be used for particular allowable inputs to the program. So the way this software generally works is it looks at what's being typed in, tries to figure out which particular opcode or command or argument it's looking at, and then it assigns a numeric value, and these are the values that are in the data sheet for the Signetics device, and the text is again taken out of the Signetics datasheet. If you do try and do this, just be warned there are some errors in the 8X300 datasheet, and you do need to kind of pick your way through it fairly carefully, otherwise you end up with nonsense coming out of the assembler. But each of the allowable strings, so AUX in this case, is used to determine the numeric value that should represent in the assembled instruction. So in the structure we have a string of characters, and we also have a value that is associated with each of those strings. So this pair we have here is the string itself and the numeric value that string represents. And using this method means that you can easily add different strings, and you can repeat the values. So for example, we can have lowercase and uppercase, and we could have any combination of these, and it just makes the whole thing much easier to future-proof if you want to add things or change any values, and it's quite easy to do that. And there are several of these arrays of structures depending on what they're for. So we have one really for each of the allowable fields within the instructions, and each of those fields has an allowable range of values, and that's what is in each of these structures. And we can use these as lookup tables once we've determined what was typed into the particular field. And again, this text is what's taken directly out of the datasheet. We then have some housekeeping. This is to allow us to save the project, open the project, and also it has some logic in here to flag up whether you want to save the project if any changes have been made, but also to control the status of some of the buttons and dialogues in the software. So for example, there's no point having the save button enabled until you've loaded a file, and there's some logic just to make sure that the application behaves in a fairly sensible manner. Same with the clear button. When you clear the project, it just disables some of the buttons to make sure that the buttons won't work when there's nothing entered into the edit or editor. There's a change control flag. This is what is used to determine if any changes have been made to the project since it was opened. And then we get to the assemble button handler. So this is the button that you would click on when you want to start assembling the project. It's relatively complicated but fairly simple in its structure. So the first thing it does is just initialize a few of the values that are used, and it sets a label on one of the text labels on the form so that it indicates what the current status of the assembly process is. So it's 2 pass process, so it starts off by saying it's pass 1. We'll have a look at that in a few minutes. It then disables the buttons on the interface. Again, this is to make sure that you can't click on the assemble button and then click on it again. The assembly might take a minute or so for very big projects, and if you were to click on the button more than once the assembly started, then as soon as it's finished the first assembly it would start another one. So this just makes sure that the application behaves in a sensible and logical manner. Then initializes some other values, clears the edit boxes, just make sure that the application is ready to start the assembly process. If a file name's been provided for the output file, this is the binary output file that will be used to program the ROM. If a file name has been provided, then it will try to create the file itself. So if you don't want to create the file, you just clear the file name and it won't create the output file. It then starts pass 1, and pass 1 is to build the symbol table. So although this is not a compiler, it's only an assembler, I wanted to be able to use labels for addresses. We'll have a look at how this works in a few minutes, but essentially a label is just a position in the code that you can jump to by name rather than having to work out the address. It will allow you to jump to particular addresses as well if you enter a hex value instead, so you can either enter a label or a hex value. It just made it easier to do it that way, or at least in terms of using the assembly. It just complicates the code a little bit. It then starts and works its way through all the lines that it finds in the editor, and it does it one line at a time, and each line is handled one character at a time. So it starts off by getting the first character in the first line. You can have the code effectively scroll through as it's being processed, and again we'll look at this in a few minutes when we watch the application running, or you can disable it, and this is just to make sure that the current active line is visible on the screen. If you don't set this, then nothing will appear to change on the screen, and we might want to have it scroll so that we can see any current errors. It then starts processing the current line, and it keeps doing this until it gets to the new line character. So each line is a standard Windows editor, so it starts off with a return and a new line in that order. So the new line is the last character on each line. It keeps track of the length of each line. We'll come back to what that's for in a few minutes. And also it checks to see if we've started a comment. If we've started a comment, it effectively has to still work its way through to the end of the line, but it ignores all the characters because, for example, a comment could contain a valid opcode, but you don't want it to be handled as an opcode because it's only within a comment. So it needs to keep track of whether or not it's within a comment, which is what this comment flag does. And hence, if the comment flag is set, then it does not run the main part of the pass 1 loop. If the flag's not set, it then goes through looking for any labels. It's looking for labels and valid opcodes. Even in the first pass, it still needs to look for valid opcodes because it has to work out the address that will be assigned to each label. That's kind of the point of the label. So it's not just finding labels, it's trying to find the label and the address of that label. That's not the line number of the label, that is the opcode address. So it goes through, it does that for any labels it finds, it puts them into a symbol table array, and that will contain the structures, or an array of structures for the labels. And that structure is fairly straightforward. It is just as you can see here, it's defined as symbol, and again it's a string of characters up to 20 characters long, which is the maximum length for the label that I've decided to use. You could change it to anything you want, of course, and then the address for that label, and then I've defined an array of those structures. It's 200 in this particular array, so you're limited to 200 labels, but of course you could change this to any value that you want. Okay, so when it's going through looking for valid labels, it checks to make sure that the character that it's found is part of, or it's a character that's allowed for labels, and you can change this to whatever you want depending on what you decide you're going to allow in a label and what you're not going to allow in a label. So it's you don't need to do this, but if you don't do this, you could end up with all sorts of weird and wonderful labels that could cause you other problems. So for example, you don't really want to include the new line character in the label, because that will in itself make the behavior of the application very unpredictable. And if a label's too long, it will throw up an error, and I've defined a show error function rather than putting in all the error code in each of the positions where errors could occur. It just simplifies the overall code and keeps it smaller. It goes through and does this until it gets to the end of the editor, so when it's processed all the lines that are present. And then once it's done all that, we end up at the end of the first pass. Now there is quite a lot of error checking in here. There's some formatting to make the output look nice. So again, it's not critical, but it's just I kind of like having applications look fairly neat. And so we end up down here. So we'll try running it up to this point. So we'll run up to the end of the first pass, start the application, we'll load an example program, a fairly short program, and we'll try running this, and all the symbols found will be put into this central pane, and then the application should halt. So it's now run through to the end of the assembly, and if we go up and look at the symbol array, we can see it's found a number of labels. So it puts them into this table, and it assigns the address that it's found to each of them. Again, this is not the line number, this is the opcode address for the particular label. Okay, so we'll reset the application. So once it's gone through the first pass, it then moves on to the second pass. This is where it gets a bit more complex. The structure of the loop is the same. It's going through and looking at each line and each character in turn, and it processes the line one character at a time. Again, it needs to know if it's within a comment. There could be opcodes and labels and whatever else within a comment, so it's got to make sure that it doesn't get fooled into processing an opcode that's simply part of a comment. Also, the various opcodes in this processor can have different numbers of arguments. So they could have 1 argument, 2 arguments, 3 arguments, and the form of the instructions is also a bit odd. in that the position for the value, so for example if you've got a hex value to enter into the argument, it's not always in the same position in the instruction. They do tend to move about. So that's taken care of. If we look down at some of the instructions, or rather some of the functions that I've defined, you can, if we look down, I'll scroll down. So for example, for this particular function, notice that there is a second argument, which is a numeric value, and that is just telling the function that it's calling what position the parameter is in. So that's the whether it's in the first argument position, the second, or the third. And that just means I can have one function rather than one separate one for each of the different locations where a particular argument might reside, because the actual process is the same. It just needs to know where it is. Okay, scroll back up. So the first part of this loop is going through, and it is basically extracting all of the opcodes and arguments from a particular line. And the easiest way to see what's going on here is to come down and see if we can identify what has been captured for a particular pass. So again, we'll come down, we'll run the application, and so we've run down to this point. It's gone through the processed the first line where it found anything of interest. If we go back and we look at the instruction, then you notice there's nothing in this. So most likely this was a comment. So if we went further down, it would ignore this. You can see here it's got this test to see if it found any arguments, it's argument index, and it needs to be greater than 0. If it's not greater than 0, no arguments were found, and hence it wasn't an opcode. So we'll run back round to this point again. Okay, so in this case the argument index is 4. That means it's found an instruction or an opcode, and there are 4 values that it's found within that. So it'll be the opcode and 3 arguments. And to see what it is, we can just go back and look at the instruction structure itself. So you can see here that we have the opcode in the first position in the structure. We then have a value which is 03 hex. The next argument is a string, that's one of the assembler strings, and then the last argument is another numeric value. So in other words, this is an XMIT opcode, and we have the 3 arguments that were supplied with it. If we now go back and look at the application, then we'll see that if we start scrolling down through here, the first valid instruction we can find is this one, which is XMIT, and you'll notice that the arguments are identical to those that we found in the code. And the way I've written this, it's not fussy about the spaces. You can use comments, brackets, tabs, whatever else, and it will still successfully extract the opcode and the arguments correctly. And the reason I did it that way is because some of the formatting of the assembler opcodes is a bit odd in this particular data sheet. So for example, looking at this one, you notice that 2 of the arguments are enclosed within one set of braces. So I had to cater for that, and as I said, also the things such as hex values are not always in the same position. So if we look at this one, notice there's a hex value at the end, but in this one there is a hex value at the beginning. So there's a kind of a mishmash of the way that the instructions behave or are structured within this particular processor, or at least the data sheet and the way that it defines the instructions. And I wanted to stick to the data sheet just to make sure that this assembler worked the way that the instructions in the data sheet are laid out. We'll come back to the rest of this in a few minutes. But what it does, it goes through and it does that for all the opcodes it finds. The next part of the loop is to handle the opcode and the arguments that it's found. So it checks to see what the opcode was, that's the opcode field in the instruction structure that it's found, and then based on that it will call a handler for that particular opcode. If we scroll down to the first one, then it's this, and this is the handler for the move instruction. This is a fairly simple one in terms of the structure of the handler. It just calls a few helper functions, tells them where the particular field is. So this is the check S handler, and in this case the S parameter is in parameter position 1, and it's not always in position 1, which is why we have this extra index number. Checks there are no errors, then moves on to the next field, so it checks the RL field. If there's no errors, it moves on, checks the D field, and so forth. And then if that's all fine, it returns, ends up back here, and assuming there were no errors, it carries on. If there was an error, then it flags this up, shows the error. We'll come and look at this function in a few minutes, and then it aborts the operation. The rest of the functions are fairly similar. Some are more complex than others because, as I say, if we look at this, for example, these are the two basic formats for this particular instruction, but there are variations to this as well. So I had to kind of build in that flexibility within the assembler. So in other words, in this particular instruction, we can either have 2 arguments or 3 arguments. That means that there must be a way for the assembler to basically determine the difference between the two. So it does that with the argument index. So when we enter this, it will run one of 2 main loops. It will either run this one if there are 3 arguments, or this one if there are 4. The number of arguments, of course, also includes the opcode. And this really then just goes through in a similar way to the move handler, and it just passes each of the fields and handles it in the way it needs to create the output value. Some are more complex depending on the nature of the instruction, but they'll really do a similar sort of thing. The jump is just the 2 arguments including the opcode instruction. But it's complicated because I wanted it to be able to use labels as destinations for the jumps. So it will either look at the argument that's been provided as it being a hex value for the target address, or if it's been provided with a label, it will look up the address that was saved in the label symbol table that we looked at earlier. And then it will jump, or rather it will use that value for the target address when it's creating the instruction. These are the handlers for the various fields, and it's really just looking through the symbol arrays that we looked at the beginning. There are a few conversion routines to convert between integers and octal, or integer and binary, or integer and hex. We've then got the show error function, and as I said, I put this down here because I didn't want to have to duplicate this code maybe 100 times where the errors could be displayed. And also because I wanted to be able to highlight the source code line that was causing the problem, and so the easiest way to do that is to have this in a separate function. So if we now look at the application running, so we'll get rid of the compiler and we'll start up the application. Okay, so what we have here is the application interface, and the way this works, as I've shown before, is you load your test code, or you can just start typing it in. In this case, I'll load a very simple example, just a handful of lines, and this is just a mixture of sort of random instructions or opcodes and comments and labels, just so that I can run some tests on it. And if we click on the assemble, then notice we've got an error here and it's saying label not found, so there's a lot of error checking in this now. And also notice down here this line is highlighted red, and this is of course where we're getting the issue. So it's trying to find this label, but if we look through the label or symbol table, notice that label doesn't exist, and so that's where the error is coming from. And the way the application is structured, it tries to help as much as it can. So if we now click into the editor window, it will automatically select that line irrespective of where I click. So it's now selected that line. Okay, so what we can do now is we can of course simply create that label if we want to, and then we can recompile the project, and you can see this time it's successfully completed the compilation. Like I said, there's a lot of error checking in here, so if we try to enter the same label more than once, for example, and then try to assemble, it's telling us we've got a duplicate label, and it's again highlighting the line that's causing the problem. So you can just come in, modify that, and then it should compile successfully, which it does. It also highlights in this table any changes we've just made. So in this case it's showing us this is the modification we've just created, and then we get the output file, but we also get the binary output file as well. So if I bring up the folder that this is in, I'll delete that file, but if I now run the assembly again, notice that the file reappears, and this is a binary file that can be put directly into the ROM. So if I call up the programmer, we open that particular file, notice this is now the correct ROM code. 16-bit values for this particular ROM, and the first one is D563, the 63 being the lower byte. And if we look back at the application, you can see that is indeed exactly what the value should be, D563. And if you've got a mind to, you can go through the binary value and you'll see that's what this represents. But also if you look at the data sheet and check it, you'll see that that is exactly what this instruction should assemble to. Okay, if we load a larger program, a larger example, so this has got a lot more. This is still nonsense, by the way, it's just a random selection of instructions. And if we now go through this, I'll change the file name and assemble, and you'll see that it's saying down here pass 1, and it does take a bit longer for larger files. Still on pass 1. I will be putting a progress indicator on here as well at some point, but it's pretty much complete at the moment. We're now on pass 2, so it's found 47 symbols, and now it's creating the output. Still on pass 2. Okay, so that's assembly completed, and if we go back to the programmer and we load that new file, and we can see we've now got that code within the programmer ready to put into the ROM. What I've been doing with this is just creating various blocks of instructions and code so I can properly test the assembler. So this arrangement here is just so I could test the formatting of this particular field. It's not something you'd normally do, but it's one of the things you do when you're writing a new application. I mentioned before we've got this scroll feature, so if we turn that on and we reassemble, you'll see what that does. What I'll also do is I'll come down here and I will enter an invalid opcode, and then hopefully we'll find that when we try to reassemble. So we'll start the assembly. So notice now it's scrolling through and showing us exactly where it is in the process. So the first pass is building the symbol table, and it's then gone back and started again, and this time it should find the rogue opcode. And so it has indeed found that opcode. And again, when we click anywhere in the application, it automatically selects the correct line for us. So we can come in, correct it, save that to our file, and then we can reassemble. So as you can see, it's not particularly efficient in terms of time. There's a huge amount we could do to optimize this in terms of the way it searches through the various arrays. But I will not be using this for very large projects, so the fact it's slow doesn't really matter. I'll be leaving that. I'm looking more for reliability than very high speed. Okay, so that's now assembled. It's found 278 opcodes, 477 source code lines, and it's found 47 labels. And as you can see, it has successfully completed that process. We'll do one more file. This is a bigger file, so this has got a lot more lines in it, and you'll see it'll start taking time once we get to much larger files. But like I said, if you wanted to, you could speed this up by just making more efficient search functions. So when it's searching through the various tables at the moment, it's searching through entire strings rather than giving up once it's realized that the string is not the right one. But as I say, I wasn't particularly interested in optimizing it for speed. It doesn't take too long. A 1K file will take about 30 seconds to assemble. And as you can see, when it's working, all the buttons are disabled. As I said, I did that just to make sure that you couldn't get bored and click on any of the buttons while it was working. Okay, so that's pretty much it for this video. If you want to see even more of this, then let me know. But I'll be using this mostly in future to get back onto our logic analyzer and 8X300 demonstration, and hopefully put together some simple code that we can use to demonstrate the hardware.